Okay. Hello, welcome everyone to the analysis section of the International Congress of Mathematicians. My name is Durut Transragan. I will be a moderator for this section. Our speaker is Professor Benoit Collins from Kyoto University, Japan. The title of his lecture is Weingarten Calculus and its Applications. For some reason, Professor Collins has uploaded in advance his lecture, so we will watch the recorded lecture now.
Yes, thank you very much for the introduction. And today I would like to speak about Weingarten calculus and its applications. So the contents of today's talks can be split into three parts. I will first describe the Weingarten formula, which is a formula to compute integrals of polynomial functions with respect to the Haar measure on compact groups. Then I will describe asymptotics of the Weingarten formula for some specific sequences of groups of interest. And finally, I will spend some times on selected applications, including free probability theory, quantum information theory, mathematical physics, and random matrix theory. So let us first recall the general setup. What we are given is a compact group. So we know that a compact group admits a unique left and right invariant probability measure, which is called the Haar measure. So namely, this is a finite measure, which has a mass 1 on the group G. And it has the property that for any Borel subset A of G, the measure of this subset is equal to the measure of any of its left or right translates. So what we can see, thanks to this, is that if I look for a set A at the collection of all its inverses, which I denote by A inverse, then this measure will be the measure of A inverse will be the measure of A thanks to the left and right invariance and the uniqueness of the Haar measure. So the goal of Weingarten calculus is to integrate functions with respect to the Haar measure mu G. And the first question clearly is which functions are we talking about? So for this, we need to narrow down a little bit the scope of the problem. And what we do is we focus on matrix compact groups, so groups which are subgroups of GLN of C with the multiplication of the general linear groups. So since they are compact, actually, without loss of generality up to some conjugation operation, we can assume that they live inside the unitary group. So a typical element U of G, thanks to this matrix embedding, can be seen as a matrix. So U, with respect to the canonical basis here, has entries Uij. And the point of view which we are using is that Uij, we view these n square elements as functions from G to C. And basically the polynomial functions which we want to try to integrate with respect to the Haar measure is a polynomial function in these functions Uij and their conjugates. So it is also possible to adopt a matrix, a probability point of view, thanks to this matrix setup. So if I have a vector valued random variable, I recall that its moments are just the expectation when defined of x1 to the k1, xn to the kn. And here what we are saying is we're saying that our vector space is going to be this one, and we take a random vector, so if you prefer a random matrix, whose distribution is given by the Haar measure on the group G. And what we want to do basically is to compute the joint moments. So here we have a real structure. So what we really want to compute is this 2n square real random variable, real part of Uij, imaginary part of Uij. So I view these guys now not as a function, but as a real valued random variable. So actually, for the purpose of computations, it will be easier to try to compute not real parts and imaginary parts, but U and U bars. So I pick an arbitrary number of K entries, which could repeat, and I look at the product, the monomial composed by Ui1, J1, Uik, Jk in U, and K prime entries also, which are completely, which could be the same or not, repeated or not, and U bar I prime 1, J prime 1, U bar I prime K prime, J prime K prime. And now I have this monomial of degree K plus K prime, which I want to integrate with respect to the Haar measure. Or if you prefer, this is a random variable whose expectation I want to take. By the way, if I'm able to do this for an arbitrary sequences, then I can completely determine by linearity the integration over all polynomials. And then since we are dealing with a compact group, I can, by approximation, deduce the value of all continuous functions. And therefore, I completely understand, completely determine the Haar measure. So to compute this, what we have to do is to use some matrix notation. So we take our generic element U in the group G as written here, and we tensor it K times, and now we take the entry-wise complex conjugate, which we tensor K prime times. So we have a big unitary which belongs to the n by n matrices tensor K plus K times, and we integrate this with respect to the Haar measure. We obtain this function Z, G, K, K prime, whose matrix coefficients are actually these functions which we want to compute. So we just take this global approach, and it turns out it's a simple lemma actually, that this matrix here, which we want to compute, has actually a very nice structure. So let me elaborate a little bit. Since G is included in the unitary group, is embedded in the unitary group, then I have V, which is to the n, which I will call the fundamental representation of G, and V bar the contra-gradient representation. And in general, for representation, I will call fix the collection of fixed points, the vector subspace of fixed points of the representation. And what one can check with not too much work is that in the case of this representation, V tends K tends V bar tends K prime, actually this matrix here, which I introduced, which is the matrix which I want to compute, is actually the orthogonal projection onto this fixed point space. So this gives us actually a technique to compute it, which I'm describing here. So we start with some notation. E1 indicates the canonical orthogonal basis of V. And with this notation, we can take some multi-index I and describe a canonical orthogonal basis of V tens K. So what I really want is do the same for V tens K tens V bar tens K prime. And I want to use some notation which will fit well with our calculation. So I take k indices I, k prime indices I prime. And I repeat, so these are going to be row indices. I repeat for column indices. And now the main thing which we need is we need to be able to describe the set, the vector subspace of fixed points. So what I am assuming, the key assumption is I'm assuming that y1, yl generates as a vector space the fixed point vector subspace of this representation. And now what I do is I create the gram matrix of this element, which I call GR. So this is the collection of scalar products with the scalar products inherited, obtained from the tensor products. And W, which is going to be a crucial matrix, is the pseudo-inverse of the gram matrix. And the integration formula, the solution to our problem is here, basically. What I have to do is, I have this I1, Ik, I prime 1, I prime k prime, which are encompassed here. I have to take each time a scalar product with respect to all generators. Same for column indices and j here. And each time multiply by these coefficients, which I obtain from the pseudo-inverse of the gram matrix. So this is actually quite a classical formula to compute a projection, which we are just applying here. Is a formula to compute a projection when we don't know an orthogonal basis of the spanning set. So that's actually the Weingarten formula. And let me make first some historical remarks and comments. This formula had not been written as such, but this coefficient had already been discovered in the past. And actually, I think they were first described by 't Hooft in the early 70s, and they were described more systematically by Weingarten in the 70s, at least for some series of large unitary or orthogonal groups for n large enough when the degree of the polynomial is not too big. And it has been rediscovered and reused sporadically for 20 years on until we started to study it more systematically. So for interesting applications of this general theory to be derived, some conditions must be met, which I write here. First of all, we should be able to describe a generating family of the image, or else we go nowhere. And in general, this has to do with some kind of representation theory. So this would be either some kind of Chauvel duality theory or some Tanaka-Crane derivative or so. Then one should hope that the gram matrix should be easy to compute of these elements, and if possible, meaningful from a geometric point of view. Like we would hope that it has a geometric interpretation in terms of loops or something like this. Also, this quantity here, which is needed here, should also be easy to compute. So in general, this would be a Kronecker delta. And somehow we are just narrowing down all the depth of the calculus to understanding what Wij is, which is the inverse of the gram matrix. So basically, it's how to compute the inverse of a nice matrix and get some interesting information from it somehow. That's one way to describe Weingarten calculus if one would like. So let's look right away into some examples. I will focus actually on the orthogonal group and the unitary group. So for this, I need to introduce this notation of pair partitions on 1K. So you see, I have, this is typically K over 2, a partition into K over 2 pairs. So this is empty if K is odd, and if it is even, the number of elements is 1 times 3 times ... K minus 1, which is K double factorial. And we also introduce, given a pair partition, a notion of multi-index Kronecker function whose value is going to be 1 if inside each block the value of the index of the two indexes of the multi-index are the same, and 0 in all other cases. So let's just look at an example here. K equals 4. So I here is I1, I2, I3, I4. It's the multi-index I1, I2, I3, I4. And here this is the pair partition which has 1 and 2 together, 3 and 4 together. So the delta of this partition with I is 1 if and only if I1 equals I2 and I3 equals I4. So next we can use this to send actually elements of P2K, to embed elements of P2K in V tensor K times, where V, remember, is the K-fold, is the fundamental representation. So again, that's the formula. And let's look at one example. You see, I take the same arch, the same pair partition, 1, 2, 3, 4. And then what we do is we sum over all elements. EI, EJ is the canonical basis of V. So this is EI times EI, EJ times EJ, sum over all IJ. So you see how this works in general. And once we have this, actually, we are able to describe the Weingarten formula in the case of ON and UN. Remember that what we need to be able to do is to compute this and this in a nice way. So that happens to be the case. The gram matrix of these two elements, E pi prime, is actually the number n to the number of loops generated by pi and pi prime put together. And for a general index, actually, EI, so this is the canonical basis of the tensor product, scalar E pi, this is just a generalized Kronecker delta index. So that part is all right. And now we can describe simultaneously the orthogonal case and the unitary case. The orthogonal case, what we do is we just look at all E pi for pi belonging to the pair partitions. And this generates actually, this is a generating family of the image of the matrix which we want to compute. So here you see I have a 0 because I don't care about the bars in the case of ON, because U equals U bar, so I don't need that. So actually with this, I'm able to compute in principle. So I have a matrix here, I compute its inverse, and I have a formula which describes completely the integral over the orthogonal group. For unitary case, we need to have as many U as U bars, or else there is a U1 symmetry which will kick in, which will give a 0 integral. So in this case, what we do is we don't take all the pair partitions, we just take the pair partitions which match one of the U's with one of the U bars. So actually, this is in bijection with the permutations on K prime elements. And once we take these subsets of the pair partitions, so when which matches the U's and the U bars, we are not matching a U with itself, or never matching a U with itself, or pairing a U bar with itself. Then we obtain the generating family, and then we have the answer also for UN. So this is the general formula, and it turns out in the unitary case and also in the orthogonal case that we can do some interesting representation theory out of that. So let me describe a result in the unitary case. So I first introduce some notation. We have the group algebra here of the symmetric group on K elements. And sharp sigma is what I call the number of cycles in the cycle product equation of a permutation. And if lambda is the group elements associated to sigma, the permutation sigma in the group algebra C of Sk, we just look at the sum of n to the number of loops of cycles of sigma, lambda sigma. And it turns out that we can, generally, it has a pseudo inverse, a G inverse, which we call W, whose coefficients are W. And what we observed with Schniadi around 2005 is that actually what we call the Weingarten, what was actually originally called Weingarten function in some cases by Weingarten, is actually this function which I wrote earlier in the theorem, and is actually this function which is here. So all these functions are the same, and they have actually a very neat character expansion in terms of characters of the symmetric group and dimensions of irreducible repetitions of GLN, or of the unitary group. So that was for representation theoretic formulas. And there are also combinatorial formulations, combinatorial representations. So let us look at, for a permutation, at the following problem. We would like to write sigma as a product of L transpositions, where the transpositions satisfy that their biggest elements, which would be JP here, is weakly increasing. So the number of solutions to this problem is related to a problem of Hurwitz counting. So this is some kind of Hurwitz number actually. And what initially Novak observed in a slightly different context, and that then I observed together with Matsumoto, is that we have this actually the Weingarten formula, the Weingarten function is actually almost a generating function for the number of solutions of this Hurwitz problem. And interestingly, actually, similar results hold true for orthogonal and also symplectic cases, both at the computer level, but also at the level of representation theory. And so this is a handful of papers which I did with Matsumoto. Okay, so before I start speaking about application about asymptotics, I'd like to make a digression in the quantum group case. So Voronovich introduced compact matrix quantum groups in the 80s, and he proved basically that they behave like compact groups. They in particular, they have an existence and uniqueness of a Haar measure, although it is also non-constructive initially and non-explicit except for characters. And together with Banica, what we observe is that the Weingarten formula extends mutatis mutandis to Voronovich quantum group. And in the case of 3 orthogonal quantum group and 3 unitary quantum groups, which were introduced by Wang and studied further by Banica, together with Banica, we obtained 3 Borel type theorems, so asymptotic freeness results for the entries of quantum groups. However, the character expansion which I described earlier does not really exist for quantum groups, but with Brannan we figured out that the combinatorial expansion which we found with Matsumoto also extends to some quantum groups, for example the 3 orthogonal quantum groups. So this time it involves non-crossing pair partitions, which are very heavily used in free probability theory. And we actually used this 3 or 4 years ago to solve some problems about the positivity of the dual of the temporally lib basis, which was some problem asked by Jones like more than 1 decade ago. So now back to classical compact groups, and I would like to start saying some things about asymptotics of Weingarten functions, because somehow being able to say precise things about it is the hard part and the interesting part. So I will actually just focus on the leading order for explicit statements before moving on to applications, and in particular focus on the unitary case. So the first thing is that there is one explicit formula, but basically only one, if you take one full cycle, so remember the Weingarten function is defined on permutations. I mean, it boils down to defining it on permutations. And basically, if I view this as a function of n, for where n is the n of the unitary group un, it is actually a rational function in n with a 2k minus 1 poles, which are separated between k minus 1 all the way down to minus k plus 1, with this leading term, which is up to a sign, the Catalan number. So for more general permutations, the situation is more difficult, but there are some interesting approximate results. So if sigma is a disjoint product of two permutations, then actually the Weingarten function of sigma will be the product of Weingarten function of sigma 1 and sigma 2 up to some defect, which actually turns out to be understood as well, but we already have this asymptotic multiplicativity property, which actually was already observed earlier. So somehow this result generalizes some result which was observed by Bian in 1998, where he actually described this leading term in terms of a Bian-Speicher-Möbius function, which was also heavily used in free probability theory. So now let me start speaking about some applications, subjective selection of applications, depending somehow on which kind of asymptotics we look at. So if we just focus on the most basic asymptotics of the leading order, we can already obtain we can get lots of mileage from this. Asymptotic freeness of Voiculescu, and already quite a few results in quantum information theory. If we go to arbitrary order asymptotic freeness, which includes higher order freeness, then we can do interesting things about matrix integrals and tensors. Then, if we do uniform asymptotics, we have results in quantum information theory. And center plus uniform, this gives some results about strong, like operator norm convergence in random precision theory, which I would like also to describe a little bit. So, what we're doing now is we're doing a little bit of random matrix theory. So I have an index set I, and for this index, and for each, I am picking matrices in which I call AIN, which are n by n, and I am just assuming that whenever I take a sequence of indices, the normalized trace of the product admits a limit as n goes to infinity. So this is what Voiculescu calls an asymptotic distribution in the sense of non-commutative distribution. So this assumption is going to repeat it once more for another family. And what Voiculescu proved is that if asymptotic distribution, the existence of an asymptotic distribution works both for AI and BI, then it is also going to work for the extended family AI and BJ rotated globally by a Haar unitary matrix. And this big extended family has also almost surely, as n goes to infinity, a joint asymptotic distribution, which can be computed, and this is governed by asymptotic freeness. So the most general version of this result can actually be proved manually, numerically, thanks to Weingarten calculus. So interestingly, a variant of this, which is not random, can be obtained and has some interesting consequences in representation theory. So this is a series of works which I did with Schniadi and Novak. So here what we are doing is we look at the enveloping algebra of GLN. So I take two tensor copies of it, and I look at some matrices which have value is there. So it's an n by n matrix which has value in this twofold tensor product. So EIJs are the generators of GLN, capital EIJ are the canonical elements, and I take these two matrices, so where EIJ goes on the second leg for 1 and on the third leg for 2. And the result that we have is as follows. If I take K1n and K2n, two characters, two sequences of characters associated to irreducible finite dimensional rotations of GLN of C, and I assume that the characters are actually normalized, and I assume that A1n and A2n have joint limiting distribution. Have a joint, limiting distribution with respect to normalized trace times K1n times K2n, which is a state here. So this is non-competitive variables. Then jointly, they are actually asymptotically free. And this can be proved again by Weingarten calculus, almost directly. And so here again, Weingarten calculus, for these purposes, generalizes previously techniques which were introduced previously by Bian, relying on character calculations, and it gives refined new information about the statistical properties of factors in the decomposition of two irreducible rotations of GLN of C. So this result looks like some non-commutative probability result, but actually it's possible to apply it to say, to do some probabilistic representation theory. So another application which I want to mention quickly of Weingarten calculus and of the most basic asymptotics of Weingarten calculus are quantum information. So let me just describe one matrix model on which Nikita and I have been working quite a bit. So we have two parameters, k, which is an integer, and t, which is a parameter between 0 and 1. And what we do is we pick a random isometry from Cpn to Ck and Cn. So k is fixed, n and Pn go to infinity at the same pace, and this pace is Pn over Nk. The ratio remains close to t. Now what we have is we have this random map from Mpn of C, from the Pn to Pn matrices to the n by n matrices, which is obtained by just send the matrix here in Mk times Mn and then trace out k. We're just left with the n by n matrix after tracing out. So this is actually a random map, which is actually called a random quantum channel. And what we're doing is we're going to apply a variant of this to something which is the Bell state. So the Bell state is the orthonormal projection on two sum of EI times EI. So where EI is the canonical basis as previously. And so what we do is we apply phi times phi bar to the Bell state. So phi bar is the same as phi, where after replacing u by u bar. And what we have is that the non-zero eigenvalues of this converge almost surely towards this quantities t plus 1 minus t over k square, and all the other ones are 1 minus t over k square. So this looks like maybe a slightly strange result at first time, but this is actually one of the results which is used to understand the problem of violation of the minimum output entropy, the violation of the additivity of the minimum output entropy, and we need to make some Weingarten calculation to understand this. So this has been quite an important problem in the last decade or so in quantum information theory. So next, if we dig further into the asymptotics, and if we look at the higher order asymptotics, so here I'm going to introduce the classical cumulants in the non-normalized traces of random matrices. So here you see I have random matrix as before, and I take some L1 products here, L2 products, and so on and so forth, and I take the cumulants of the trace of these people normalized with this factor here. Then, if we assume that this limit exists, then we speak of higher order limits. And together with Mingo, Speicher, and Schneerdy, what we proved is that, again, if I have a family A which has a higher order limit and a family B which has a higher order limit, then the family A and globally rotated family B also admits a higher order limit. And in addition, there exists a combinatory rule to construct the joint asymptotic correlations from the asymptotic correlations of each family, and this rule extends freeness of Voiculescu, and this is called higher order freeness. So this actually generalizes some results which I obtained earlier, again, with Weingarten calculus, where we proved that the formal convergence of arbitrary matrix integrals in non-commutative polynomials, and this result itself extended previous convergence results for Harish-Chandra, Itzig, and Zuber integrals. And there is an ongoing work like a series of work that started together with Razvan Goura and Luca Lioni, where actually we extend this whole program to the context of random tensors, and all the theory generates very well. So we have a whole new notion of generates Hurwitz numbers. So if you're interested, you're encouraged to take a look at that. So there are many developments in this direction as well, on which I will not spend time today. Because now I want to start speaking about the uniform estimates. So all the estimates which I gave so far said, okay, let's pick sigma, and as n goes to infinity, this is the kind of behavior which we have. So with the original Weingarten formulas, it was actually very difficult to obtain some satisfactory uniform estimates. But with more works, actually with the new formulation, the new combinatorial formulation of Matsumoto and I, we have actually been able to observe that the asymptotics of Weingarten formulas are actually uniform to a very up to a polynomial extent, actually. So K here is the group in which the permutations work, and if I go quite far, actually, the estimate here actually turns out to be a uniform, and we actually already started to have some applications of this in a quantum information theory for something which is called the problem of the area law. So there is one paper with Perez Garcia and Gonzalez Guillen there, but there are more applications to come, which I will describe in the context of a centered version. So the centered version is if I center a random variable by subtracting its expectation, I could decide to make the same Weingarten calculation, the same Weingarten, the same calculation, and it turns out that there is a very similar Weingarten formula here, and this is a joint work with Charles Bordenave, where actually we introduced a notion of a lonesome block. So you see here I have T blocks, okay? I have T blocks which correspond to T centerings, and a lonesome block is a block such that the permutations which are involved here stabilize the block, and the Weingarten estimate says that in general the decay is L minus K, where this is the degree of the polynomial, and here this is the distance between permutations is what we already have from previous Weingarten formulas. But if we make some centering, we get some additional decay, which is 2 to the number of lonesome blocks, which actually allows us to go further when we have this polynomial estimate. So let me explain what kind of application we get from this Weingarten formula. So I recall here what we saw a bit earlier in a slightly different context, the non-commutative distribution of Voiculescu for non-commutative probability spaces, so Unitary star algebra and a trace. And together with Mal, we introduced a stronger notion of convergence, of strong convergent or convergent norm, which is that you don't have only the convergence of the monomials or polynomials pointwise, but you also have the convergence of their norm. And what's an application of centering that we proved with Charles Bordenave is as follows. If you fix two integers q plus and q minus, then you look at u bar I times q times u bar I times q plus. So this is a big matrix which belongs to m n times q minus plus q plus, where the ui's are all IID Haar distributed matrices. And then if I look at this on the orthogonal of fixed points, then this is strongly asymptotically free. And well, this has many consequences in representation theory, but all this seems to indicate that the main obstruction to strong convergence in operator, so the convergence in operator norm, seems to be the presence of a trivial representation in a sequence of representations. So what we have actually is that the fixed points seem to be the only problem. So how do we prove this? Well, we prove this with a moment method. So a moment method would consist in taking some matrix whose norm we want to understand to a high power, to a power L, which will depend on n. And if the power is large enough, then the estimate which we have here is actually going to be good enough. So we need to have some uniform estimates. And however, if we want to do it with a non-commutative polynomial, that's not going to work. That's too difficult. So we have actually to do something which is called a linearization trick, which was introduced by Pizier and then Hargroup Torbjörnsen. So with matrix-valued linear polynomials, but even that remains too hard. So what we did is we introduced some non-backtracking theory. Namely, we introduced some operator B, which lives in a bigger space, which involves some matrix elements with some non-backtracking component here. And this matrix here, thanks to this structure, works very well with moment techniques. And this is going to be, the moment strategy is going to be a viable strategy if we manage to relate the spectrum of B to the spectrum of what we want to compute. And that happens to be possible thanks to one theorem which we proved here, which I'm maybe going to skip in part. But so there is a relation between operators of this type and operator of that type, and it is possible to invert the relation. So if I have a matrix A, I can create a matrix B, which will allow me to do the question which I want to make. And so this can be, all this can then be done thanks to the help of centered Weingarten estimates, which I mentioned earlier. So let me finish with some concluding remarks. So this was just a subjective overview in 45 minutes of what are the recent applications and developments of Weingarten calculus, but there are much more actually. Like this has slept completely out of control. So there has been some early applications. A former student of mine has been doing some applications to finance. There are potential applications to algebra. So there is a reformation of the Alon-Tarski conjecture by Landsberg-Kumar, which relies potentially on Weingarten calculus. Very interesting applications to discrete group theory by Maggie Puder. Application to random geometry by Maggie and his collaborators. Recent application to quantum to artificial intelligence, and the list goes on. So I will stop here. Thank you very much for your attention.
Okay. Thank you very much, Professor Collins, for a very interesting talk. Thank you very much to all who have been watching this lecture. Bye.